Hi everyone, I hope you are all safe and healthy. I'm Martin Robert and I'm going to talk to you about our paper, Tree Bark Re-identification using a deep learning feature descriptor. The plan for this video is to highlight the important part of our paper. So we are going to make an introduction, then discuss the methodology, the dataset we built, our result, and give a short conclusion. So let's begin with the introduction. The problem we investigated is the re-identification of tree bark surfaces. That in turn allows tree re-identification. As an example, the 6 images shown here come from only 3 distinct surfaces. Could you guess which are the pairs of images corresponding to the same bark surface? Here is the answer. They were already paired together. As you have seen, the difficulty to match bark images together comes from their self-similarity and the significant change in their appearance that occur when we vary the illumination angle and viewpoint. Reliably re-identifying bark surfaces would improve the SLAM algorithm by associating bark images to landmarks in the map, like in this example. It could also improve lumberyard logistics by enabling the tracking of felled lumber from the forest to the woodyard. In this methodology section, we will get a quick overview of how we described and compared images. We decided to use local feature descriptor to work on bark surface re-identification. We also made the hypothesis that traditional handcrafted descriptor will struggle with this task, so we also compare learned descriptor. To represent handcrafted descriptor, we chose the common SIFT and SURF. For the learned descriptor, we use DeepDesc and our own version that once we train with bark data, we rename DeepDesc Bark. We also adapted ResNet and SqueezeNet to receive 64 by 64 pixel input and output a 128 dimensional vector. Finally, after having trained them with bark data, we renamed them DeepBark and SqueezeBark. To compare two images, we first build a global visual signature. This signature has a first component key, which is all the key points found in the image. Then, we use a descriptor to describe all these key points and create the list of description V. Finally, from the list V of description, we build a visual bag of words B. To compare a query image IQ with a database image I, we associated every description from V in VQ with a V in VI and filtered the matches with either the lower ratio from SIFT or a geometric verification based on a nearest neighbor check. The number of remaining matches then serves as the matching score G. We also use the bag of words to compare a query image with a database image by using the distance between them as the score G. However, in this video, we will focus on the geometric verification since it gives the best results. For other results, please get a look at our paper. This dataset section is an important piece of our work because, to the best of our knowledge, already existing bark datasets are for 3 species classification only, while bark surface re-identification require a dataset to be indexed by instance and allow image registration. So, we begin by collecting the bark ID dataset. This dataset is composed of 50 red pine trees with 2 surfaces per tree, totaling 100 red pine surfaces. And we also collected 50 elm trees with, once again, 2 surfaces per tree for a total of 100 elm surfaces. For each surface, we took 12 images with different variation of illumination and viewpoint. In the figure below, we can see actual bark images taken from the bark ID dataset. You can also see our wooden frame with its fiducial markers. These markers not only allow to easily crop the image, but also allow to infer camera plane transformation between two images, which is essential for a bark-aligned dataset shown later. To make a more challenging experiment, we also collected additional negative examples. This data is composed of 25 elm trees with 30 images per tree for a total of 750 images. Note that these images have some physical overlap, but importantly, none of these images were used in the query dataset. With the bark ID dataset and the ability to calculate spatial transformation between images, we built the bark-aligned dataset. This dataset is made of 64 by 64 pixels image patches. Across the 12 images of a single bark surface, we found approximately 800 to 1000 distinct key points. With the spatial transformation between the 12 images of a surface, we have been able to make 12 crops per key point, as shown in the figure below. This is really important since this dataset allowed us to train Learn Descriptor using metric learning. Note that you can contact us if you think of using our dataset. Now let's look at some of our results. Well, almost. Just before, it is important to note that we perform a classic image retrieval task with 11 relevant images for each query. Also, we reported our results using average precision recall graph based on the ordered score of every query. Now, let's really look at some results. Here, we compare our different descriptors on a set made of 50 red pine bark surfaces and 50 elm bark surfaces for a total of 100 surfaces. With 12 images per surface, our test set had 1,200 images that we all use as a query against the rest of the set. As mentioned earlier, this is a result using a geometric verification to calculate the matching score. In this setting, we see that the bark clearly dominates the other descriptor and show great precision even with high recall. For this experiment, we wanted to know if Learn Descriptor could perform well on unseen bark. For this, we trained the descriptor on one tree species and evaluated it on the other species. Our result here showed that our best descriptor, deep bark, performed worse than previously, but still achieved good precision on either of the three species. Here, we evaluated the performance of SIF and deep bark when adding negative examples. To do this, we use only elm bark since our negative examples are solely elm bark. We also cut every images of elm in our bark ID dataset in half to double the amount of elm bark images we had. So by removing red pine and doubling elms, we stayed at 1,200 images used as query, but this also made the task harder. In the results, we see that SIF loses performance as more negative bark images are added, while deep bark keeps a nearly constant performance. It really showed how deep bark paired with geometric verification is a reliable way to re-identify bark surfaces. So now for a quick summary. With our paper, we show that three bark surfaces can be re-identified, meaning that we can then track individual trees much more reliably, either in the context of SLAM or for supply chain logistics. And we also showed that Learn Descriptors are necessary for this task. Finally, there could be a lot more to be done. For example, we could add more data in experiment to generalize on more tree species, try other key point detector, or even use advanced geometric verification. Also, more realistic experiments could be done, like test on a bigger dataset, add occlusion like snow, leaves, ripped bark, or even investigate partial bark intersection in images. So that's it. Thank you for listening to this video and stay safe.